Yeah, thanks so much, Alison. It's really been wild relative to expectations, how much things have accelerated in the FRO space. So just before I start, has everyone already heard about convergent research and focused research organizations? Like, who has heard of FROs? Okay, so not everyone. Great, it won't be entirely redundant. I will go a little bit into the intellectual history so that it hopefully gives something new even to those who know all about FROs. So anyway, other than the iTunes, what you see here is a Venn diagram that we like to use to define what an FRO is. In short, it's a non-profit R&D project that is tightly scoped, has a 5-year timeline, although there can be exceptions around the edges, and has a clearly defined goal to deliver a public good for a field of science or technology. So we've heard about road mapping and tech trees. I too am very fond of these exercises. You have probably all seen these tech trees from the game Civilization, and like the hope would be that our civilization would be navigating towards future technologies in a similar way. First, look down the technology tree, figure out what is important, what might be impactful, and which steps of getting to those important technologies are hard and rate limiting, and prioritize those. And in fact, you probably all have seen that the process looks a bit more like this. People jump at what is short-term profitable or cool, or in academia, prestigious. And so I hope Adam won't be mad that I put in some screenshots. I'm not sure if you're seeing them well, but these are screenshots from a doc that he wrote about 2018, as Alison mentioned. That was called Projects That Should Exist. So Adam worked in the Ed Boyden lab on. I hope he won't be mad at me for putting in this picture. So Adam worked in connectomics at the Ed Boyden lab and tried to develop BCIs in kernel, Brian Johnson's Neurotech startup, and then we also overlapped at DeepMind where he was working on memory algorithms. Anyway, so he's had a relatively wide array of interests, but across these interests, he's seen a very specific type of gap in the incentive structures in academia and industry. And so this doc that I'm taking screenshots from had a short list of projects that really should be happening, but somehow aren't. So the first one was the connectome of a mammalian brain. So Adam was involved in from Ed Boyden's lab in the BRAIN initiative, which distributed funding among American labs that worked on connectomics, that is building a map of the connectome of the brain. But none of the labs were necessarily incentivized or resourced enough to really build the tools to make connectomics scalable and cheaper for all of the other labs. And if you ask any single lab, they would agree that in an ideal world there would be a project that is really well resourced and has professional engineering support that would deliver these tools, and then all of the labs would benefit from those and accelerate their progress. But there wasn't necessarily a coordination mechanism for building such a set of tools. Some other items from this doc that might be close to chemical 3D printing. Eric's idea. This one hasn't happened yet in an FRO form, although I'm hopeful that at some point there will be a program or FRO towards this. Yeah, what are the reasons that these aren't happening by default? So this is Adam's favorite slide from or favorite picture from an academic conference, where you see this is from a neuroscience conference where you see each academic with a single poster, and there's this like one-to-one mapping between the researcher and the project, like sometimes you get collaborations of multiple people, but very rarely a long-term sustained engineering effort towards a goal that is doesn't deliver a publication within 2 to 3 years and doesn't advance the single academic careers of the people involved. And so when we were at DeepMind, we've seen that the AlphaFold team, I'll jump to this slide. The AlphaFold team took a different approach than academia and also than a typical startup. They picked a problem that doesn't necessarily have a clear profit motive, which is protein structure prediction. You've probably all heard of AlphaFold. Protein structure prediction. Basically, all academic labs in protein engineering have been trying to solve this problem. Many pharma companies you would expect would have the incentive to do this, but it actually took a tightly focused team of about 15 people with engineering and support and resources and burning a lot of compute to actually get to the outcome of minimizing errors on structure prediction. So the question that Adam asked was, can we get these systems engineering projects that we've seen in physics, in space exploration and telescopes and these large-scale projects that coordinate many scientists and engineers behind a single goal? Can we get this also in biochemistry and other areas that don't have this tradition? And what he estimated is that for many of these, tens of millions of dollars could be sufficient to really accelerate the given field. So just to get a sense of how calibrated you are, how much do you think the Manhattan Project cost in today's dollars? Any guesses? Yeah, about like order 100 billion. Like, it depends on whether you count it as proportion of GDP or adjust for inflation, but 45 to 100 billion is the right order. The Human Genome Project. There's a nice way to remember it. It's yeah, 3 billion. So it was exactly $1 per base in the human genome, and so George Church, Adam's PI, actually had this criticism of the Human Genome Project that it focused a bit too much on this outcome rather than building the tools that would make it cheaper. Big inspiration for the FRO model. Anyway, so. To give you the sense of scale, what we're proposing here is that we can get philanthropically funded projects that are on the $50 million scale, which might seem like a big number for some of you, but for some of you, it might actually seem very, very small. They are medium-sized projects, and you can see it in comparison with Human Genome Project here. It's roughly the size of a DARPA program, but the key difference here, conceptually, is that a DARPA program works with many external performers or a number of external performers, private companies, labs, and coordinates them behind a single goal. Whereas the FRO has a single team that is focused on delivering a tool or data set, etc. So what makes a good FRO? We want to be maximally catalytic and pick projects that can be done in academic labs and in the private sector because of profitability. And so the model that we settled for is 5 to 7 years, $30 to $50 million, 15 to 25 people, and yeah, as I mentioned, we've had a lot of unexpected success in getting some of these funded. The Brain Connectome tool building project is underway under the brand of E11. It's our first FRO, and since E11, we've somehow gotten to 9 FROs, I believe, including single cell model organism, domestication, for lack of a better word, single cell protein sequencing, acceleration, and many others. Happy to talk more, but want to emphasize this is one tool in the toolkit. It's not necessarily the way to do all of science. It's actually, in my opinion, a way to do like probably less than 5% of science and technology development. But it's on the margin a very key gap that we should fund more of. Yeah. Yeah, sure. All right. Yeah, shout out to my former colleague Milan, who made this. To walk you through it, the key features are the production of public goods rather than something that can be funded in a private setting through VC. Startup-like tight coordination and focus on a goal, which you don't necessarily get in academia outside of rare exceptions, and the scale, which is on the scale of an industrial R&D lab or a project within that. So yeah, you can ponder the diagram.